What's up, Sioux High Earth Science students? This is Mr. McLeod again. Welcome to our next set of podcasts dealing with the structure of the Earth and plate tectonics. I hope you have as much fun listening and writing notes as I have making these. So get your notes out, something to write with, and let's shake it, baby, shake it. See what I did there? You know, shake it like the earthquakes that form due to the for Pete's sake, let's get started. Okay, first of all, I'd like you to get this diagram into your notes. Now, you don't need to include the layers of the atmosphere. You already have those. Just draw the pie slice like you see it here and label correctly. This is the pie slice. Now, if you want to add the kind of bullseye looking thing, piece of the Earth, fine, but the pie slice is what we're going to talk about in more detail. Now, the interior of the Earth is divided into layers based on specific chemical and physical properties. Get that in your notes. Now, I'd also like you to get a basic description of each of these layers in your notes. Then we'll talk about each layer in more detail. Okay, let's start from the outside and work in. The Earth has an outer solid crust that you see here. The crust is made mostly of silica. Write that down. Then as we move from the outside in, we see now, we find the mantle, which is divided into two sections, the upper mantle and then the lower mantle. And finally, we have the core comprising a liquid outer core that is much less viscous. Viscous means it's not like water, it's more like oil. It's kind of slimy type thing. So the liquid outer core is much less liquidy than the mantle. And there's also a solid inner core. So get those descriptions in your notes, and now let's talk about each one more specifically. Okay, now we're going to do the opposite. We're going to work from the center of the Earth out. So here we find the inner core. The inner core is primarily solid sphere, about 1,220 kilometers in radius, and situated at as close to the center of the Earth as you can get. Now, based on the abundance of chemical elements in the solar system, their physical properties, and other chemical constraints, the inner core is believed to be composed primarily of nickel-iron alloy with small amounts of some unknown elements. Write that down. So the inner core is made mostly of a nickel-iron alloy. That's what we need you to know about the inner core. Now, how about the temperature? The temperature is estimated at about 5,000 to 6,000 degrees Celsius. Get that in your notes. And the pressure is thought to be 330 to 360 GPa, which you don't really understand. But what you will understand is it's 3 million times that of the atmosphere on the surface. So get that in your notes as well. Then there's the liquid outer core, which is about 2,300 kilometers thick. And like the inner core, is composed of a nickel-iron alloy, but with less iron than the solid core. Now, seismic and other geophysical evidence indicates that the outer core is so hot that the metals are in a liquid state. Write that down. Next, we move to the mantle. The mantle is approximately 2,900 kilometers thick and makes up about 70% of the Earth's volume. Write that down. The mantle is divided into sections based on changes in its elastic properties with depth. In the mantle, temperatures range between 5 and 900 degrees Celsius at the upper boundary, with the crust to over 4,000 degrees Celsius at the boundary. Write that down. All right, let's look at the crust in some detail now. First of all, you should know that we actually live on the crust. So those of you who cut the crust off your peanut butter and jelly, you better rethink that. Now, there are actually two different types of crust, continental and oceanic, as you can see here in this slide in the upper right corner, continental and oceanic. I want you to make a column for each in your notes, and let's use these columns to list the characteristics of each kind of crust. Since each has different properties, they behave in different ways. So make sure you have two columns, one for continental crust and one for oceanic crust. Okay, first let's look at the continental crust you see here, and then let's list the characteristics in your notes. Continental crust forms the land, otherwise known as the continents, as the name suggests, that we see today. Get that in your notes. Continental crust averages about 35 kilometers thick. Write that down. Although under some mountain chains, crustal thickness is approximately twice that thickness, and we'll talk about that here in a little bit. Okay, continental crust is less dense and therefore more buoyant. Buoyant means it can float than oceanic crust, so get that in your notes. Now this becomes very important when we start to talk about earthquakes and interactions between tectonic plates. Now, continental crust also contains some of the oldest rocks on Earth. Write that down. Remember from the Birth of the Earth video that ancient rocks older than 3.5 billion years in age are found on all of Earth's continents. Okay, now let's look at the oceanic crust. Oceanic crust is seen right here, right below the continental crust. Now, as the name already suggests, this crust is below the oceans. Write that down. Now, compared to the continental crust, oceanic crust is thin, only about 6 to 11 kilometers. Write that in that column. However, oceanic crust is more dense than continental crust, and therefore when the two types of crust meet, oceanic crust will sink underneath continental crust. So write that down. It's less dense than continental, and it will sink below continental when they meet. That's very important. Now lastly, the rocks of oceanic crust are very young compared with most of the rocks of continental crust. Write that down. In fact, they're not older than 200 million years, which makes them a lot younger than the continental crust. As of right now, we really can't go to the center of the Earth. So if we can't go to the center of the Earth, except in fictional movies, how do we know what the internal structure of the Earth is like? Well, we need to use our geophysical imaging techniques to model what's going on below our feet. For example, when there's an earthquake, it sends out seismic waves, also known as shock waves. Write that down. Now, seismologists, those that analyze those shock waves, write that down. Seismologists can measure the time it takes for these waves to reach seismic monitoring stations set up around the globe. Now, the machine that measures seismic waves is called a seismometer. Write that down as well. Now, the different layers in the earth have been inferred using the time of travel of refracted and reflected or bent seismic waves created by the earthquakes. You see some of those right here in this diagram. And you see how bent they are. What that means is that changes in seismic velocity or speed occur as the waves pass through different materials. Write that down. So these waves are bent because there's changes in velocity or speed as they pass through different materials. Make sure you get that down. So measuring these changes tells seismologists how many layers there are and the thickness and physical properties of each layer. Also write that down. Now, the interesting thing is we need not wait for earthquakes to happen. What happens now is explosions can be set to cause shock waves to pass through the crust, simulating an earthquake. That's how they measure now what happens when an earthquake happens without waiting for an earthquake to happen. So write that down. So they artificially set explosions that send shock waves through the crust, and then they use that equipment to measure it. So make sure you get that in your notes. Now, there are other geophysical methods. For example, measuring different gravity, magnetic and electrical anomalies by air and or satellite can help to reconstruct shallow crust features. We can also go and examine rocks at the near surface of the crust through fieldwork, drilling boreholes, and mining. Now, I'm betting that all of you have at least heard of the idea of plate tectonics. Now, if you have, take a minute and write a brief description of what you think plate tectonics is in your notes right now. And then we'll try and explain it and see how close you are. Okay, if you look at this map of the world, you may notice that some of the continents would fit together like the pieces of a puzzle. For example, the shape of Africa that you see here, if we could move this piece to the right, you would see that they look like they might fit together like a puzzle piece. Well, this is because they did used to fit together like a puzzle piece. Write that down. The Earth as we see it today was not always like it is now. Land masses have pulled apart and joined together by the process we call plate tectonics. Also get that in your notes. So it's the process by which land masses are pulled apart and joined together. We call that plate tectonics. Now, the Earth's crust is divided into 12 major plates, which are moved in various directions. Write that down. So 12 major plates that are moved in various directions. Now, you can see now some of the boundaries in this map. For example, you see the Eurasian plate here. You see the North American plate we live on right here. So you see the Pacific plate. That's where a lot of earthquakes and volcanoes happen. We actually call this the Ring of Fire, and we'll talk more about that later in class. Now, it's this plate motion that causes three kinds of interactions to occur between plates. So let's get these in your notes. One, it can cause plates to collide. Two, it could cause them to pull apart. Or three, it could cause them to scrape against each other. So make sure you've got those three descriptions in your notes. Each type of interaction causes a characteristic set of Earth structures, otherwise known as tectonic features. Write that in your notes. Also write that the word tectonic refers to the deforming or changing the shape of the crust. Now, what in the world are these plates made of, you say? Well, tectonic plates are made of what's called the lithosphere. You see this word right here. Here's how you spell it. The lithosphere, which is a combination of the crust and the extreme upper mantle. So you see now here the crust and the extreme upper mantle. They make up the lithosphere. Okay, now let's move down to the asthenosphere. Now you see the spelling right here for asthenosphere. The asthenosphere is still part of the upper mantle, but is located just beneath the lithosphere. So you see here, the lithosphere is the crust and upper mantle, and then the lower mantle here is the asthenosphere. Because it's still part of the upper mantle, it's very hot. In fact, it's so hot that it's about 1 to 5% liquid. Write that down. That's very important. So this asthenosphere layer is 1 to 5%, depending on where you are in the Earth, liquid. Now remember, because it's still part of the upper mantle, it's 95 to 99% solid. This liquid that is formed allows part of the asthenosphere to flow. Write that down. So the liquid, the 1 to 5% liquid, allows the asthenosphere to flow. Now again, this becomes very important when we start to talk about volcanoes. Beneath the asthenosphere is the rest of the mantle, which is completely solid. Now that would be this layer right here, which is still completely solid. But the asthenosphere now has a liquid component to it. So make sure you get that in your notes. Okay, now let's look at how and why tectonic plates move. The question of how tectonic plates are moved around the globe is answered by understanding, boy, can't talk this morning, by understanding mantle convection cells like the one shown here. So you see a couple of different mantle convection cells diagrammed here. So we want to follow the arrows and talk about why these arrows occur. So that's where we're going. And those arrows now will determine how these plates move on the crust. Now it pays to remember that heat rises when trying to understand these convection cells. For example, have you ever opened an oven door and felt the blast of hot air coming past your face? For me, it always fogs up my stinking glasses. Now, just like the hot oven, in the mantle, hot material rises toward the lithosphere like hot air rising out of an oven. Write that down. That's very important. So this hot material now rises toward the surface just like that hot air comes out of the oven. Now, when the hot material reaches the base of the lithosphere, it cools and sinks back down through the mantle. So you can see this arrow, when that hot material now hits this cool layer, it sinks back down. Remember, hot rises, cold sinks. Now make sure you write that down. What happens is a continuous cycle is then formed where cool material at the base of the lithosphere is replaced by more hot material, and so on, forming a large convection cell, as pictured in this diagram. Get that in your notes. extremely important that you understand why mantle convection happens. So hot air goes up, hits the cool lithosphere, is sent back down, is heated again, etc., etc., etc. Now what I want you to do is write this little picture of a convection cell in your notes and make sure you can explain it. Now the end result of this slow but incessant movement in the mantle is that it causes the rigid tectonic plates to move or float around on the Earth's surface, albeit at a really slow rate. Write that down. Now, a good example of how this works, let's say that you made some vanilla pudding. And when you're done making the vanilla pudding and let it cool, you set some pieces of bananas on top of that pudding. If you then jiggled the container the pudding was in, the banana slices would move, or you could even move them with your fingers. Get this example in your notes, because this is the best model of what the plates look like on top of that liquid part of the asthenosphere. What's your favorite flavor of pudding? Mine most definitely is butterscotch. Okay, that's part one now of our discussion of plate tectonics and the structure of the Earth. So go ahead and submit your notes to Moodle, and then go grab that study guide on part one and do the questions. Talk to you soon. Bye.